ion product constant. Now let's look at what this is. It is Kw. So how do we get this Kw? First, let's look at the auto-ionization of water, because water auto-ionizes naturally. So we're going to look at our water here, obviously in a liquid state, and another water here in a liquid state. Why are we using these two water molecules as our reactant? Because in the previous video we touched briefly on acids and bases. See the link in the description for this, where we saw how if one behaves acidic, simultaneously another one acts basic. So if either of these, let's just say this one here is the acid, this one here is the base, we can see on the product side that will be resulting in a hydroxide ion and a hydronium ion and a hydroxide ion. Why is this the case? Well, if this here is our acid, which one are we going to associate it with? Are we going to associate it with this one over here, or are we going to associate it with this one over here? Well, if this here is an acid, it means it must have donated or lost a proton. Okay, and in the previous video we looked at how the hydrogen is pretty much a proton. So if it releases or loses this H over here, what do we end up with? We have our hydroxide here, because there's only one H now. Okay, so this here, okay, what would this be? This would be our conjugate base. And this one here, right, the base added that hydrogen. So what would this one be? Right after it is formed, the resulting substance that got formed after the hydrogen was added, this here would be the conjugate acid. So now that we have that out of the way, we obviously know that for our equilibrium constant, we would have to have the products on the top and the reactants on the bottom. If you don't know why we are doing this, see the previous video on the equilibrium constant. Link is in the description. So I'm going to be putting the products on the top. And of course our reactants here on the bottom. Okay, obviously these here are aqueous and these here are liquids, and remember these concentrations remain constant if we're dealing with solids or liquids, so we would have to integrate this and get rid of this so that it can be integrated within the KEQ. So in order to get rid of this and only have this in our equilibrium expression, because this is the only one that we only want gaseous and aqueous molecules, so then these would have to be removed. So we just have to multiply by whatever our denominator was. Okay, that way these cancels out. If you do it on the right side, you got to do it on the left side. There we have it. So now obviously these integrate, so this becomes now our Kw, which is what we're trying to talk about, right? Our ion product constant. Our ion product constant is represented as Kw, and it's pretty much just going to equal to our products. Now, why is this important? Well, we have to know that our units play a part. So of course this here in concentration, right? So this here will be technically moles per liter. Technically this one here is also moles per liter, but we cannot forget that here, this Kw, okay? Remember, we integrated this into our KEQ to become our Kw. So technically we could actually look and zoom in on this Kw as this H2O, right? It is also in moles per liter, multiplied by this H2O, also in moles per liter. So technically these moles per liters, if they multiply, they become moles per liter squared. So we could actually write that down over here. So our Kw, okay, let's zoom in further in on it. So rather than right now labeling it as Kw, let's label it as KQ, because I want to take a first look at these H2Os, okay? These H2Os and KQ before we zoom back out into Kw. So this H2O molecules, okay, is technically mole squared over liter squared, because these are being multiplied by this KQ, right? And we're going to do the same thing over here actually. When you multiply these two things together, of course you're going to end up just getting whatever value on the inside. Okay, we're not going to assign a number, okay, but obviously whatever number this is, whatever this number is, they multiply, it's going to create some sort of product, and then of course we can just put mole squared over liter squared for the whole thing. Now if you square this and you square this, you're pretty much just left with one molecule, okay, one molecule of this H2O concentration being ionized to produce whatever this one is here. Okay, so here I'll just write it out in case it's a little messy over here. So moreover, we have one molecule of this H2O over here. It's ionizing. That's what we're putting our equal here, right? It is ionizing and produces. What do we have on the right side? Okay, what is being produced? One molecule as well of H3O, our hydronium, okay, because we have one of them over here. And another one molecule of hydroxide, which we have over there. And since we know that this KEQ multiplied by this H2O integrated together is known as this Kw, our ion product constant, this means that this Kw is also equal to our hydronium and our hydroxide concentrations multiplied together as a product. It's also worth to mention here as a note that this H3O plus and this OH minus product is equal to 1 times 10 to the negative 14. And of course this would just be in mole squared over liter squared, okay? Because obviously this is moles per liter, this is moles per liter, they multiply, you're going to get that, okay? Mole squared over liter squared. Since we deduced that this H2O is equal to our H3O times our OH, and Kw is equal to this H3O times OH, what does this mean? It means that our Kw is equal to 1 times 10 to the negative 14 is the actual auto-ionization of water. Now, what can we conclude with? Well, we already know that our Kw is equal to the product of our hydronium multiplied by our hydroxide over here. But we also deduced that one molecule of H2O ionizes for that same product, right? Hydronium times our hydroxide. But we also note down here that our hydronium times our hydroxide, newly introduced, is now 1 times 10 to the negative 14 moles squared over liter squared. How can we wrap this all together in a nice little bow? Well, we could also just now say that Kw, okay, is equal to 1 times 10 to the negative 14, because as we see here, this is equal to this, and this was technically this anyway, so we're just putting this and this together right over here. But we also realize that this, right, is equal to this. One molecule of H2O ionizes and produces this, multiply that. So what does this mean? This Kw here, okay, is the ion product constant of water, okay? It's the auto-ionization of water value. Lastly, since Kw is equal to, like we've said, the product of hydronium and hydroxide, as you can see that they are right beside each other. They are not dividing one another. If you want to see in the previous video where we looked at the ideal gas law rate of reaction, we noticed that the pressure and the volume were inversely proportional because they were multiplying beside each other. Okay, the link is in the description if you want to see more examples of that. The same concept applies here. Okay, they are beside each other, so they are inversely proportional. Okay, so maybe I'll write here inversely proportional. So what does this mean? This means that if we multiply these two things together and they equal our kW, and we've reiterated that our kW is this value over here. Let's write it down here again. 1 times 10 to the negative 14 is equal to this times this. What are their specific values? Okay, maybe I'll just put here in question mark. Okay, what are their specific values? Well, what times what is going to give you 1 times 10 to the negative 14? Of course, it's just going to be 1 times 10 to the negative 7. Okay, I mean, an easier way to kind of look at that is because obviously you have these two things that we are trying to figure out. Okay, if we don't know, you know, what the heck these are, you would just obviously here just square root it. Okay, you square root that, it's going to give you 1 times 10 to the negative 7. Okay, so that's why these here are our values. Again, of course, these are in concentration brackets, so we could also just deduce here that the concentration of both the hydroxide, so let's say that this one, okay, and the hydronium, which would be this one here, are technically 1 times 10 to the negative 7 moles per liter. So I'll just put this here. Therefore, the concentration of hydronium is 1 times 10 to the negative 7 moles per liter, and the same thing, and the concentration of hydroxide is also 1 times 10 to the negative 7 moles per liter. Now, if the concentration of our hydronium is greater than our concentration of our hydroxide, it is acidic. It's an acidic solution. If, however, the hydronium here is greater than the concentration of our hydroxide, it's obviously going to be basic. And if they are equal, should be pretty obvious, it's neutral. It's also important to note, in a strong acid, the concentration of the acid, I'll abbreviate it here with these concentration brackets, the concentration of the acid is equal to the concentration of our hydroxide ions completely, because it dissociates 100%. Okay, so what do I mean by this? If you had 1 mole per liter of, let's say, HCl, okay, 1 mole per liter of HCl, it technically has 1 mole per liter, so exactly the same value of H3O plus. Okay, I mean, technically I can get rid of this, right? So 1 mole per liter of H3O plus. Similarly, in a strong base, the concentration of the base is equal to the concentration of the hydroxide ions. Okay, also because, okay, you can already see here, because it dissociates, 100%. So another example, if we have 1 mole per liter of, let's say, NaOH, okay, what does this have? It has 1 mole per liter of our OH minus. Now, if additional acid is added, what do you think would happen to our hydronium? Do you think our hydronium concentration, here I'll put here, do you think our hydronium concentration would increase, or do you think it would decrease? Obviously, it would be increasing, okay? Our hydronium ion would increase, and this would also mean that the hydroxide concentration would then decrease, okay? And vice versa. Okay, what do I mean by that? So if additional base is added, the concentration of the hydroxide ions would increase, and of course the concentration of our hydronium ion would then decrease. Now, as long as temperature remains constant, because remember, the only thing that affects the equilibrium, our EQ, was our temperature. So as long as the temperature remains constant, our Kw would always equal that, that value of 1 times 10 to the negative 14. So I'm just going to put here on the side. As long as temperature remains constant, Kw is equal to 1 times 10 to the negative 14. Okay? Always. This is based on the Chatelier's principle, right? Now, in case you want to see these guidelines be put into action, let's have a look at a few practice problems to see how they're executed. So this question is asking for the hydronium ion concentration. Well, we already know that Kw is equal to 1 times 10 to the negative 14, right? Okay, in moles squared per liter squared, but we'll get rid of the units for now. We'll just figure it out at the very, very end, okay? And it has a concentration, right, for the hydroxide of 0.0025. Wait a minute, didn't we already know that our concentrations for both our OH minus and our hydronium here was 1 times 10 to the negative 7? Okay, this one here as well, 1 times 10 to the negative 7. Okay, this was moles per liter. Okay, moles per liter. How come our hydroxide ion here is at 0.0025? This number here is incredibly much greater than what it was supposed to be, okay? Which would be 1 times 10 to the negative 7. That's what we've looked at in terms of our derivation of Kw. Well, what did we just previously look at as a little guideline? If there was an increase in hydroxide concentration, based on the Chatelier's principle, what would happen to our H3O plus? This would decrease. So what we should be seeing when we get our answer over here for our hydronium ion, rather than it being anywhere close to 1 times 10 to the negative 7, it should decrease a lot, because obviously this value here increased a lot from our baseline over here. So whatever value we get for hydronium, it should decrease a lot from our baseline over there. So let's see and put it into practice. We know that our formula here was this. Our Kw, we'll sub it in over here. And our hydroxide, our hydronium, we have no idea. For our hydroxide here, it was 0.0025. Let's obviously divide this accordingly so we can get rid of it. Goes away, goes away. What do you end up getting for our hydronium? You get 4 times 10 to the negative 12. Okay, obviously it's in concentration bracket, so this would be in moles per liter. As you can see, this value much smaller than 1 times 10 to the negative 7. Makes sense. Verify that the hydronium ion, okay, in a concentration of a solution at 25 degrees containing this many hydroxide ions is actually this value. Okay, so we know that our answer is supposed to be 2.2 times 10 to the negative 14. Let's see if it works out. Let's use our same formula. And then let's put in our values. Our hydronium here, still unknown. Our hydroxide over here, 0.455. Just divide this by 0.455, do the same thing over here. What do you end up getting? And 2.2 times 10 to the negative 14 occurs in concentration brackets over here. So this would be moles per liter. As you can see, they match up. This is correct, makes sense. As you can see, also, because this value over here is very, very large, okay, it's a lot greater, okay, than 1 times 10 to the negative 7. This value here should be much, much smaller than 1 times 10 to the negative 7. Of course, times 10 to the negative 14, very, very small. Makes sense. This here is a green question of the day. Not too hard. Please pause the video, give this a try yourself. I'll be giving you the answers shortly. This This is the answer.